So I want to do this one. I want to do it with a full-on quadratic formula. And I want to give you a shot, couple-minute head start on me, all right? Here's our reaction. I want to know what is the equilibrium concentration of A and B if we're starting with 1 molar A and no B. So you should be able to predict what direction we're going to go. The equilibrium constant for the reaction is 2 times 10 to the negative fifth. So I want you to do a mass action expression, write an ice table, okay? Start plug it in and see if you can't, whatever you got to do, right? Solve the quadratic formula, see if you can't get X, and then get the equilibrium concentrations. And then I'm going to teach you a shortcut, which is pretty cool. So go ahead. But we're doing it without the shortcut first because we want to prove that the shortcut works and we get about the same answer. All right, you keep on working. If you haven't finished, I'm just going to go ahead and get started here. Keep on going if you haven't finished. So hopefully you got at least this far. My mass action expression is going to be B squared over A. My ice table is going to have 2 rows, a row for A and a row for B. Initial concentration of A is the 1 molar. And initial concentration of the B, there's none of it, 0. What's going to happen? A is going to go down because it's shifting right. And B is going to go up by 2x. Hopefully you got that 2x on there. Now we're going to plug these values into the mass action expression. We know the equilibrium constant is 2 times 10 to the negative fifth. And we're going to solve for x. There we go. Pro tip for you folks. When you plug that 2x in, make sure you put it in parentheses. Because if you don't do that, if you don't put in parentheses, if you just do this, you're not going to remember that that's 4x squared, right? You're just going to have it on the x. So this would be the first area where people really go south here with their algebra. It's the quantity 2x squared. This is going to be 4x squared. So this is really 4x squared over 1.00 minus x. The next thing we're going to do, we're going to end up with a polynomial here because that's x squared. So we're going to multiply both sides by 1 minus x and distribute, and then we're going to get everything equal to 0. So if you screwed up that algebra, go back, try to fix it while I'm still going. Here we go. We should get 0 equals 4x squared plus 2 times 10 to the negative fifth x minus 2 times 10 to the negative fifth. As our check your quadratic. Did you get that as your quadratic? If you did, now we're off to that quadratic formula. So let's see if we can't plug that in. Let's see if I can't squeeze it all in here. We're going to see. So negative b, that's negative 2.0 times 10 to the negative fifth plus or minus the square root of b squared, so 2.0 times 10 to the negative fifth squared minus 4 times a, which is 4, times c, which is negative 2.0 times 10 to the negative fifth, all over 2a, which is 4. And now I'm going to try to get what's under the radical here. And if I make any algebra mistakes, y'all just yell at me. I can plug a number in my calculator or make a stupid mistake just as easy as anybody. I'm no master mathematician. People think, oh, Nate, you must be so good at math. I mean, I'm okay, but I'm not like I don't love math. Like I mean, not my thing. So under the radical, I got 3.2 times 10 to the negative fourth. So now I'm going to take the square root of that. And I'm going to get negative 2.0 times 10 to the negative fifth plus or minus 0.0179 over 8. And I'm just going to get the two possible values of x here. Here we go. I got positive 0.0022 and then probably negative that, but let's try it. Yeah. Or negative 0.0022. Now the negative 0.0022 we can throw out. You can never have a negative x. Now if they were both positive, you'd have to plug them in and see which one gave you a negative answer. That one would be wrong. One of them is going to be too big. Okay. But that 0.0022 has to be the correct value. So we're going to plug that 0.0022 into here. As 0.998 and 0.0044. And now you can always check your work. If I do this squared divided by that, I should hopefully get 2 times 10 to the negative fifth. Let's try it out. 0.0044 squared divided by 0.998. And I got 1.9 times 10 negative fifth. Close enough. It's rounding that gets us off there. So, oh my goodness. Okay. X is small assumption. Here's how it works. If, this is very, 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 very important. If the smallest initial concentration divided by the equilibrium constant, if that ratio of the smallest initial concentration divided by the equilibrium constant is greater than or equal to 500, then it is safe to make the X a small assumption. What is the X a small assumption? The X a small assumption allows you to cancel out any plus or minus X's. Not all X's, but any plus or minus X's. So, for example, see that minus X there? You could get rid of it, right? As long as you tell me X is a small assumption. This will allow you to avoid having a polynomial. You'll still have an X squared, but you can just take a square root, right? Like you don't have to use the quadratic formula. Why does this work? And we're going to go back and prove that this works here in a moment. Essentially, what we're saying here is if the initial concentration divided by the equilibrium constant is greater than 500, then what we're saying is that the amount that X is compared to that initial concentration, that X is so minuscule that the initial concentration after it gives up that little bit of X is essentially still going to be that original initial concentration. With the sig figs and stuff, it's not even going to be that impacted. Okay, so let's try this with the previous problem, okay, and I'll show you how it works and we'll compare. So for example, I'm going to get rid of all this quadratic stuff. So I'm going to go back in time here, folks. In fact, just so we're back up to speed, I'm going to erase all this stuff except for my x because I don't want to forget what it is. I'm going to compare here. Okay. If we go back, to this point where we have our ice table, we have our mass action expression, if we plug this junk in, so Kc 2.0 times 10 to the negative fifth equals the quantity B squared divided by the A, like that. We go back to this point. When you are at this point, before you're like, oh man, I got to do this quadratic craziness, you always want to see if you can make the x a small assumption. Here's how it works. You take the smallest initial concentration other than 0. So the only thing I have an initial concentration of is A. So that's 1. We're going to divide it by the equilibrium constant. So we're going to take the smallest initial concentration divided by the equilibrium constant. So 1.00 divided by 2.0 times 10 to the negative fifth. And we're going to pop that in our calculator. Go ahead and pop that in your calculator and see if it's greater than 500. And we get 50,000. That is greater than 500. Here's what we're saying, folks. We're saying this reaction has an equilibrium constant that's really small. The reaction favors the reactant side. It's got to go a little bit to the right because I don't have any B, but it's going to stay mostly on the reactant side. Because this reaction so heavily favors the reactant side, the little bit that A is going to go down isn't going to matter. Essentially, the amount that A goes down and the original amount of A are almost going to be identical. If you get a value that's greater than 500, x is small. So what happens here? I want you to write x is small, and you can get rid of the minus x that's there. If it was a minus 2x, you can get rid of the minus. You can get rid of all of them, right? Because if x is small, then 2x is small, whatever. Okay, so any plus x or minus x. Not all the x's. Like that x still stays. It's just the plus x's or the minus x's that you can get rid of. Now this super duper simplifies, right? This becomes 2.0 times 10 to the negative fifth equals 4x squared over 1. So that's really 4x squared, right? Because we got rid of that minus x. Divide both sides by 4. We get 5.0 times 10 to the negative 6 equals x squared. Then we take the square root of it, and we get, folks, 0.0022. We didn't just get close. With 2 sig figs, we got the exact same answer. Look at how much easier that was. No quadratic, right? None of that. Like, oh my goodness, was that easier. That was so much easier, okay, than having to do it that long, crazy way. So you always want to check and see if you could do x is small, right, and eliminate any x values. There is a check you can do, like at the end. I don't make, some professors make people do it. At the end of the day, if it was indeed safe to make that x a small assumption, if you take x, which is 0.022, divided by your smallest initial concentration, which was 1, multiplied by 100, it should be less than 5. Okay, essentially what we're saying is we are, by making the x a small assumption, we're saying we are okay with up to 5% error in our x values. Now, if you were taking analytical chemistry where you got a 100% know the absolute correct answer, like, no doubt about it, you're not making any assumptions, right? You're not taking any shortcuts. But if you do this with the previous problem, we get a percent of 0.223, way less than 5%.